Guys, my name is IBM and today I'm taking you into what we are going to call kinematics. Kinematics has several areas which include describing motion. We shall describe motion in terms of words such as velocity, such as speed, time, and acceleration, distance, displacement. In kinematics, we shall discuss projectile motion, uniformly accelerated motion. We shall talk about speed and velocity. We shall talk about acceleration. We shall talk about distance and displacement. And we shall also talk about the equations of motion under uniformly accelerated motion. So these are the areas which we expect to talk about or to explore under kinematics. Remember, kinematics together with dynamics are areas of mechanics. And if you're doing mathematics, especially mechanics paper 4, or mathematics paper 4, you will also appreciate the concepts in this unit because this is actually mechanics. Kinematics and dynamics are actually mechanics. We have already seen dynamics, so I want us to concentrate on kinematics. If you are doing AS physics or you are doing both AS and A level at the same time, you realize that kinematics is a very important lesson, is a very important AS concept, especially if you check the past papers, you'll notice that most of the questions of kinematics, most of the questions of mechanics require concepts of kinematics. And sometimes there is no boundary between kinematics and dynamics. So when you check the solved past paper questions, you'll find that there may not be any clear boundary between the two. So this is going to be lesson 1 of kinematics. I hope there will be around 4 to 5 lessons because I try to make it long just to ensure that I give as much confidence to students as possible. So you can always download the lessons and watch them at your convenience. You can leave a like, you can leave a comment. I'm always willing to try and rectify anything that is not very clear. Okay, so let us start kinematics. And to start with, we shall begin by talking about the learning objectives or the expected learning outcomes at the end of the unit or of the topic kinematics. So at the end of this lesson or at the end of this topic, you should be able to do the following. Number one, you should be able to define and use distance, displacement, speed, velocity, and acceleration. In other words, you will be able to distinguish between distance, displacement, speed, velocity, and acceleration. Remember, of course, in the first unit of physical quantities and units, your teacher must have told you that there are 6 vectors at AS level, and if there are 6 vectors at AS level, in this unit of kinematics, we mentioned 3 of them. And these include displacement, velocity, and acceleration. So the rest of the concepts, or the rest of the quantities you'll explore, or the rest of the quantities you'll meet in AS physics are going to be scalar quantities. Of course, there was electric field strength, but electric fields were moved to A level, so you'll not meet it in AS physics. We shall also be able to use graphical methods, or you should be able to use graphical methods to represent distance, displacement, speed, velocity, and acceleration. So we are going to describe motion in terms of graphs, such as distance time graph, displacement time graph, speed time graph, velocity time graph, acceleration time graph, and so on and so forth. So you should be able to determine a displacement from the area under a velocity time graph. Of course, it is the same concept you studied in GCSE where you said the area and the velocity time graph is the displacement. Then you should also be able to determine the velocity using the gradient of a displacement time graph, the same concept you saw in GCSE. You'll also be able to determine acceleration using the gradient of a velocity time graph. It's also the same concept you saw in GCSE. Then we shall be able to derive from the definitions of velocity and acceleration the equations, which represent uniformly accelerated motion in a straight line. And these ones are the ones we call equations of motion, which apply if the acceleration is constant and the motion is in a straight line. That is, these are the ones we call equations of uniformly accelerated motion. Then we shall solve problems using equations which represent uniformly accelerated motion in a straight line, including the motion of falling bodies in a uniform gravitational field, where we shall just consider G to be equal to 9.81 without air resistance. We shall always assume air resistance is negligible, and therefore we shall always assume that the acceleration is constant and it's 9.81. Then we shall describe an experiment to determine the acceleration of free fall using a falling body. And finally, we shall describe and explain motion due to a uniform velocity in one direction and a uniform acceleration in a perpendicular direction. And this is going to be what we call projectiles, where motion is going to be in two dimensions. So uniform velocity in one direction and uniform acceleration in a perpendicular direction. And this is what we are going to call projectiles. Okay, so let's now introduce kinematics. So what do we mean by kinematics? Let's introduce the concepts of kinematics. So at the start of physics begins with what we call mechanics. When someone talks about mechanics, what does that imply, or what comes into your mind? Physics entirely starts with the mechanics. And mechanics is a branch of physics that focuses on the motion of object and the forces that cause the motion to change. So mechanics deals with motion of objects and the forces which cause this motion to change. That is entirely what mechanics is concerned with. So that means mechanics is divided into two. There is a part which deals with the motion of objects alone without minding about what causes or what affects the motion. And there's another part which is concerned with what affects the motion. That is now mechanics. So there are two parts of mechanics. They have kinematics and dynamics. I decided to start with dynamics before kinematics, but in a normal class, it's supposed to be kinematics before dynamics. So as well, kinematics deals with the concepts that are needed to describe motion without any reference to forces, without minding about the forces or anything affecting motion. The motion of objects can be described in terms of quantities such as position, speed, velocity, and acceleration, as we are going to see. So mechanics is divided into two, kinematics and dynamics. Kinematics deals with the concepts that are needed to describe motion. So in kinematics, we just describe motion. We can describe motion using words, we shall describe motion using graphs or equations without minding about the forces or anything else affecting the motion. Of course, whatever normally affects motion is going to be the forces. They could be dissipative forces such as friction, air resistance, and so on and so forth. So on the other hand, dynamics deals with the effect that forces have on motion, and we saw this in dynamics. Effects, the effect that forces have on motion, that is now the concern of dynamics. But today we are just going to concentrate on kinematics, where we are going to deal with the concepts that are needed to describe motion without minding about the forces which are acting. Okay, so kinematics is the science of describing the motion of objects using words such as using words, diagrams, graphs, equations, etc. So in kinematics, we are just going to describe motion using either words, using graphs, using diagrams, using equations without minding about the forces or without even referring to the forces which are affecting or which cause an effect on the motion. So in other words, the goal of kinematics is simply to develop mental models to describe the motion of real world objects. So we're just aimed at describing motion in kinematics. Of course, the word kinematics comes from kine, which means in motion, or motion, in motion to be precise. So in kinematics, we are just going to describe motion. We shall not mind about what affects the motion or what is causing the motion. but we shall just describe the motion the way we see it or the way we perceive it. Okay, so the first thing we shall do, because we said in kinematics we describe motion using words, diagrams, graphs, and equations, we shall begin describing motion with words. So let's describe or talk about describing motion using words. So even a person without a background in physics has a collection of words which can be used to describe moving objects. For example, in everyday life, you talk about a body is moving fast, the car is slowing down, the car is braking. So even if you don't have any background in physics, you have a collection of words that you normally use in everyday spoken language to describe motion. So in kinematics, we want to borrow those words to describe motion. For example, going faster, a car is going faster. The car has stopped. The car is slowing down. The car is speeding up. The car is turning. And all these words are used in everyday life to describe motion. So these provide a sufficient vocabulary for describing the motion of objects. So we are now describing motion by simply using words. However, to be specific then, even though everyone even without a background of physics will be able to use these words, going faster, stop, slowing down, speeding up, and turning, and so on and so forth. For us in physics, we shall modify these words and use very specific terms such as distance and displacement, speed and velocity, and then acceleration. So we shall normally use the language of kinematics, such as distance and displacement, speed and velocity, acceleration, to simply describe motion in a more scientific way. So in this unit or in this topic, we shall describe motion using these words: distance and displacement, speed and velocity. Then we shall talk about acceleration. These are the words we are going to use to describe motion. Of course, these words, as we mentioned in the first topic, can be described as being scalars and vectors. So these words which we use to describe motion can be divided into two categories. That is, some of them are vector quantities, others are scalar quantities. Remember from your first unit of AS physics, scalar quantities are those quantities which are described by magnitude only. We don't mind about the direction, or the direction cannot be denoted. And then the vector quantities are those quantities which have both a magnitude and direction. So speed and velocity, distance and displacement, and then we have acceleration. Those are the scientific or the kinematics, the words we shall use in kinematics. That is the language of kinematics: distance, displacement, speed, velocity, acceleration. And we know that out of all these terms, displacement, velocity, and acceleration are vector quantities. Displacement, velocity, and acceleration, we know that those three are vector quantities, and therefore the rest are going to be scalar quantities, of course, not forgetting time. So a scalar quantity, as we mentioned in the first unit of AS physics, a scalar quantity has only magnitude, and a vector quantity has both magnitude and direction. So every time we talk about velocity, displacement, and acceleration, direction is very, very, very important because these are actually vector quantities. So let's begin with the first term, the first words that we shall use to describe motion so that we understand the difference between the two before we use them later on. So let's talk about distance and displacement. Of course, this is the same concept. These are the same concepts you knew right from GCSE, and we're just revisiting them. What is the difference between displacement and distance? We're going to consider the motion of an object from a point which has been labeled start up to a point which has been labeled stop. There are two ways of reaching the stopping point. Either you move directly from the starting point in a straight line to the stopping point, or you move around the red path until you reach the stopping point. But in most cases, the road or the only available path could be the red path. So what we are trying to distinguish between distance and displacement. If there is any possible way for you to move straight from the starting point to the stopping point without following the designated or without following the available red path, then the shortest distance between the starting point and the stopping point is the displacement. It is actually the straight line distance moved by an object in a specified direction. The straight line distance, straight line, in a straight line. That's why you see the green line is a straight line. The straight line distance. So it must be the straight line distance moved by an object in a specified direction. That is what we call displacement. So your displacement is the shortest direct distance. Direct. The shortest direct distance from start to stop. It is the shortest direct distance from the starting point to the stopping point. That's what we call displacement. So instead of following the red line, you just move straight from the starting point to the stopping point. So the straight line distance or the shortest direct distance from the starting point to the stopping point is what we call displacement. So in other words, displacement can be defined as distance in a specified direction, to be specific. Distance or straight distance moved by an object in a specified direction, that is what we call displacement. So an example is imagine you drive following the path below or the path besides. Imagine you drive following the path besides and your odometer goes up, that is it reads your distance. The distance you drive will be greater than your displacement. So someone looking at you directly from the starting point will see that you are closer. Yet for you who is driving, you might have driven a longer distance to reach where you are because you are following the red path. So the distance you drive will be greater than your actual displacement because displacement is the shortest direct distance from the starting point to the final point or the stopping point. That is displacement. Okay. But on the other hand, of course, we know that distance is the total length along the actual path traveled by the particle or by the body. That is the distance. We just consider the total length along the actual path followed by the object. That is what we call distance. So now we know the difference between distance and displacement. Of course, on the other hand, we also know that distance is a scalar quantity and displacement is a vector quantity. So distance, total length, or the actual length, total length of the path, total length of the actual path, followed by or traveled by the object, that is distance. The displacement is the straight line distance moved by an object in a particular direction or in a specified direction. The shortest direct distance from the starting point to the final point, that is displacement. Okay. Let's now summarize the difference between the two, distance and displacement. So to summarize this, we shall just consider a table. Distance being the total length of the path traveled irrespective, that is without minding about the direction of the motion. Of course, we know that displacement is the distance moved in a particular direction. It is actually the shortest direct distance moved in a particular direction. The straight line distance moved in a particular direction. That's what we call displacement. And we know that distance is a scalar quantity. We don't mind about the direction of the distance. And displacement is a vector quantity. Of course, both of them are measured in meters because they are both lengths. So that is the difference. That is the difference between a displacement and distance. We can also say that displacement is the object's overall change in position. Overall change in position is what we call the displacement. Okay, so to understand the difference more, let's use a simple example. So let's think of a situation where a student walks, say, 4 meters east, 2 meters south, 4 meters west, and finally 2 meters north. So if you were to sketch the path or the movement of this student, you'll notice that he has moved 4 meters east, 2 meters south, 4 meters west, and then 2 meters north. So this is how this student has moved. So 4 meters east, 4 meters west, 2 meters south, 2 meters north. So he has come back to this same point here. If I was to find total distance, then total distance will be the sum of all the distances around the path followed, because it's the total length of the actual path traveled by this object or by this student. But if I was to consider displacement, because he has come back to where they started from, it means there is no difference between where they started from and where they have stopped. So in that case, displacement will be zero even when distance is zero. So when he is finished walking, there is no change in his position because the initial position is the same as the final position. Because we have already seen that the 4 meters east would cancel out to the 4 meters west. So this would cancel out that because displacement is a vector quantity. So if it is a vector quantity, if in one direction it is positive, in the opposite direction it must be negative, so that when you sum up, they cancel out each other. And then the 2 meters south cancels out or is cancelled by the 2 meters north, so that these two cancels out, and therefore total displacement will therefore be 0. So that is what we mean by displacement. If you start from a point and come back to the same point, the displacement will be 0, but the distance will not be 0. If there is no change in direction, the displacement will be the same as the distance. For example, if I start from point A and I move to point B and I move 10 meters, with no change in direction here, the distance will be 10 meters and the displacement will also be 10 meters. If there is no change in direction, the distance and the displacement are the same. But if direction changes, the distance and the displacement would not be the same. If I moved from A to B, let me first rub off this. If I moved from A to B, let's say 3 meters, and then I moved from B to C, which is vertical downwards, and which is 4 meters. Here there has been a change in direction, so the distance would be 3 plus 4, which is going to be 7 meters. But when it comes to displacement, it is going to be the straight line distance from where I started from to where I stopped. So this will be the displacement here. So this will be the displacement. And in that case, the displacement, because this is a right angled triangle, the displacement will be the hypotenuse of this triangle, which will be got from Pythagoras theorem. So the displacement will be equal to 3 squared plus 4 squared under the square root. And this will be 9 plus 16, which is 25. So this will be 5 meters. So in all cases, the displacement is already smaller than the distance. So if there is no change in direction, the displacement and the distance are the same. But if there is a change in direction, the displacement will always be smaller than the distance. Example: a particle moves from point A to point B along the path of a circle of radius 5 meters. What is the distance moved by the particle, the displacement of the particle? So let's first have a diagram. So the particle moves from A to B. Of course, the displacement is going to be the shortest distance from A to B, the straight line distance from A to B. But it is moving, the particle moves in a circle, so the distance is going to be the circumference of this circle. So in that case, for the displacement, I don't even need to calculate anything. For the displacement will be equal to the diameter of the circular path, which is the straight line distance from A to B. Because the radius is 5, so this will be 2 times 5, which will be equal to 10 meters. That will be the displacement. But then when it comes to the distance will be equal to the circumference. It will be the length of the arc, so which is the circumference of that path. So the distance will be equal to the circumference, and this is half a circle. So circumference of a full circle is 2 pi times the radius. So half a circle, this will be 2 pi over 2, which is simply going to be pi r. So the distance is going to be pi times 5. And this will be equal to, I think pi is 3.14. This is approximate to 16. So this is approximately 16 meters. So you notice that the distance is always bigger than, or is always greater than, the distance is always going to be greater than the displacement, because the displacement is simply the straight line distance from the starting point to the final point. Yet the displacement, I mean the distance is the length of the actual path followed by the object. So you should be able to recall or to note the difference between distance and the displacement. Because displacement is a vector quantity, the displacement from A to B is actually going to be downwards. It is always towards the final point. The displacement is always towards the final point. So it is going to be downwards. For distance, we don't mind about the direction because it's a scalar quantity. So that is what we call distance and displacement. Okay, let's now talk about average speed and instantaneous speed. Remember, we are describing motion just using words. So let's talk about average speed and instantaneous speed. In GCSE still, you were able to distinguish between these two concepts, average speed and instantaneous speed. And the word average and the word instant can still hold their English meaning. So from GCSE, you recall that the average speed is the actual total distance traveled by the object over the total time taken. That is the average. We don't add speeds and divide them by 2 or divide by the number of speeds, not at all. For average speed, we take the total distance traveled by the object and we divide this by the total time taken. So if the object is moving at a constant speed, then this equation will give us its speed. If the object is moving at a constant speed, then the equation average speed is equal to total distance traveled over total time taken will still give us the objective speed. But if the object is changing, then the equation will give us average speed. So if the speed is constant, then the average speed is distance over time taken. But if the speed is changing, then average speed will be total distance over total time taken. Not total speed over total time, or not total speed divided by the number of speeds, not at all. In GCSE, you saw this very carefully, that average speed will be total distance traveled divided by total time taken, or total distance traveled divided by the total time of the journey. So that is average speed. So if you look at the speedometer like the one I have shown in this picture here in a car, the speedometer doesn't tell you the car's average speed. You don't see the average speed on the speedometer, not at all. If you look at the speedometer in front of your car or in the car, it simply tells the speed at that point when you look at it. It tells you the speed at that point when you look at it. It doesn't tell you the average speed you have been covering all throughout your journey, not at all. The speedometer will give you the speed at that particular moment when you look at it. And that's why this speed, we call it the instantaneous speed. This speed is going to be called the instantaneous at that particular instant when you look at the speedometer. At that instant, it is the speed at any instant, at that instant when you look at it. So, you should now know the difference between average speed and instantaneous speed. If I say what is the speed at 5 seconds, so you exactly look at the speedometer at 5 seconds. When I say the average speed of the journey, it means you have to know the total distance for the whole journey and the total time that it took you, because you cannot drive at the same speed from the starting point up to the final point, because there could be traffic, there could be humps, and so on and so forth. So all these factors make the speed to fluctuate between a certain maximum and a certain minimum. Of course, the top speed could be very high and the minimum speed could be very low, but the average speed for the whole journey will simply be the total distance covered throughout the journey divided by the time taken for the whole journey. Yet for the instantaneous speed, you just look at the speedometer to see the speed at that particular time. That's what we mean by, that's the difference between average speed and instantaneous speed. A few things we need to note here. Of course, the SI units of speed and average speed is the same, measured in meters per second. That one we know from GCSE. But since this is A level, you'll see several other units such as centimeters per second, kilometers per second. You'll see kilometers per hour, miles per hour, and your task will be to be able to convert these units from whatever unit to the SI unit, which is meters per second. Of course, meters per second is an SI base unit, because meters is a unit of length, which is a base unit, and seconds is a unit of time, which is also a base quantity. So meters per second are units of base quantities, so they are actually base units. And also the choice of units will depend. For example, you would probably give the speed of a snail in different units from the speed of a racing car. You can't give the speed of a snail the same unit as the speed of a racing car, because we expect that the speed of a racing car is going to be high, perhaps in kilometers per hour or miles per hour. The speed of a racing nail is going to, a snail is going to be too low. It could even be in millimeters per second. So you can't give them the same units, because the racing car is a very big speed and the snail is a very small speed. You can't give the same units for the speed of light to the speed of a snail, because these are very different speeds. The speed of light is extremely high compared to the speed of a snail. So the choice of the units in some cases may depend um, on the magnitude or the size of the quantity being measured. And this you must have talked about this under measurement techniques. So also I want you to note that in any calculations, it is always necessary to work in SI units. In many cases, you'll need to work in SI units for convenience, but sometimes it may not be necessary, especially when there's a possibility of units cancelling out. But in many cases, it is going to be convenient for you to work in SI units, such as meters per second. Okay, so that is average speed and instantaneous speed, or that is briefly what we could say about speed and average speed. We are still going to explore more about speed, but before we go into the details, let's briefly remind ourselves or talk about how to determine the speed. Because when you reach A level, if you are doing both AS and A levels at the same time, there is a paper called paper 5, which is planning, analysis, and evaluation. So you must have ideas about taking measurements of several quantities in the laboratory to be able to plan experiments. If you have all the apparatus in the laboratory, you will be able to carry out some of these experiments. So let's talk about measuring speed or determining speed. So to determine the speed of something moving, you need to know the time taken. Of course, we need to know the time, and we need to know the distance between two fixed points. So to determine the speed of something moving, you need to measure the time taken between two fixed points. And if you know the distance, then you will use, of course, a stopwatch to know the time. For time in the laboratory, time we could use a stopwatch, or you could use a stop clock, depending on the magnitude of time. Alternatively, you could use light gates if the time is very, very small. So in the laboratory, to measure time, we could use a stopwatch, a clock, or stop clock, or light gates. Then distance in the laboratory, we could use a meter rule, or you could use a tape measure. That is in the laboratory. If the distance is extremely small, you may use a micrometer, screw gauge, digital vernier caliper, and so on and so forth. So to determine the speed, we need to know the time, either using a stopwatch, stop clock, or light gates. We need to know the distance between two fixed points, either using a meter ruler or a tape measure. So the limitation of this method is that it only tells you the car's average speed between the 2 points, but you cannot tell whether it was increasing its speed, slowing down, or moving at a constant speed. So measuring by knowing the time and the distance between 2 points, the only thing we can obtain is the average. This only gives us the average speed. And this is the problem now. Knowing the time and knowing the distance will only give us the average speed. That is a limitation. It only tells you the car's average speed. It only tells you the object's average speed between two fixed points. But you cannot tell whether it was increasing its speed, slowing down, or moving at a constant speed at some point. All you know is the average speed, because you know total distance it is going to cover or it covers, and total time it has taken to cover that distance. That is a limitation. However, it doesn't stop us from discussing some of the laboratory methods that we expect to use to measure the speed of an object, or to determine the speed of an object, say in the laboratory. So let's explore some of them, and the first one is going to be using one light gauge. One method that I could use to determine the speed of an object in the laboratory could be using one light gauge. So I am going to consider a trolley like this one that I've just used in this diagram. So to measure the speed of, say, a moving trolley like this one here, a falling mass, it is in the lab, some of the following methods are going to be used. And I'm saying the first method is going to be using a one light gate. Of course, the most important thing here is to determine the time. The light gate is connected to a timer, which is very, very important. So all I will need to do is to know the length of the card, which I have attached on the trolley. And I will measure this length using a ruler, could be a meter ruler. If the card is very small, to improve accuracy, I may decide to use a digital vernier caliper. So I am going to measure the length of the card because this card is going to intercept. The card is going to intercept the light gate for a certain length of time. And the time it takes while intercepting the light gate is going to be the time I'm going to consider for the motion. Then the length of the card is going to be the distance. So using the formula using the formula speed is equal to distance over time, then I'll be able to estimate the speed. I'll be able to estimate the speed, which will actually be the average speed of this trolley. So in this method, the timer starts when the leading edge of the card breaks the light. So as soon as the leading edge of the card reaches or breaks the light, the timer starts. And I expect the timer to stop when the end when the end of the trailing edge of the trolley passes through. So the timer will now show me the time it has taken for the leading edge to pass through and the trailing edge to pass through. And that time is going to be the time for my motion. So in this case, the timer or the time shown is the time taken for the trolley to travel a distance which is equal to the length of the card which I have attached on the trolley. So the computer software, of course, can now calculate the speed directly by dividing the distance by the time. So if I know the length of the card, which will be the distance, and I look at the timer to know the time, then the average speed is going to be the distance divided by the time. That's one method. Another method, I could employ two light gates instead. I could employ two light gates. So in this case, I'm employing two light gates to measure the speed. So the first light gate will be broken when the trolley just cuts or just passes through. When the trolley passes the first light gate, the timer starts. And when the trolley passes the second light gate, the timer stops. So what I need is to measure the distance between the 2 points where the light gates have been placed, and this is going to be D. So the timer will give me the time, and of course I'll calculate the average speed from the distance, which is the distance between the two light gates or the two positions of the light gates, divided by the time. So we are saying that in this method, um, the leading edge, the leading edge of the card in the figure, this should be besides, breaks the light beam as it passes the first light gate, and this starts the timer. Then the timer stops. The timer stops when the front of the card breaks the second beam. So when the front of the card breaks the first beam, the timer starts, and when the front breaks the second beam, the timer stops. And therefore, the trolley's speed is calculated from the time interval and the distance between the light gates. So if I know the distance between the light gates and the time interval between the first light gate and the second light gate, then I can obtain the average speed from distance over time. So if you have a light gate in your laboratory, you can try to perform this, but I can show you this in a simple animation or simple demonstration here. So let's see a simple demonstration of using two light gates in the laboratory. So here we have one light gate somewhere here and another light gate placed at the other end. So this is going to be the first light gate. Both of the light gates are joined to the timer. And we have our, I think this is called a trampoline. So we have a light gate here and we have a light gate the other side. So we just release our object so that it passes through the trampoline. I mean, it passes through the first light gate and it passes through the second light gate. And then all we do is to measure the distance between the first light gate and the second light gate. Because the time is shown on the screen or on the timer, then we just find the average speed. But remember, the disadvantage of this method is that it doesn't tell you whether the object was speeding up, slowing down, moving at a constant speed, and so on and so forth. However, it just gives you the average speed between the 2 points. That is the limitation of this method of using timers. So I expect that a basic school laboratory should have light gates like these ones and a timer. So you just set up the experiment like that, and then you measure the distance between the two light gates, and then you also may determine the time the object takes to move through the first and the second light gate, and you obtain what we call the average speed. So that's one method using light gates. Let's also talk about a method which uses what we call a motion sensor. Of course, a motion sensor must be connected to our computer or a data logger so that the data logger can be able to process and determine the speed of a moving object. The object in this case must move towards something which senses. Basically, this uses most likely ultrasound. So the motion sensor is going to transmit regular pulses of ultrasound to the object or to the trolley in this case. And what happens is that when the ultrasound reaches the object, they are reflected back to the motion sensor. So it detects the reflected waves and determines the time they took for the trip to the trolley and back. And then it passes the information to the computer or the data logger. And then the computer or data logger will now process the distance. It will deduce the distance from the motion sensor and it will now generate what we call a distance time graph. So from the distance time graph, we can now determine the speed. So that's how the motion sensor works. It is placed next to the object and sends ultrasound waves or sound waves towards the object, and then it receives the reflected waves. For it to determine, it detects the reflected waves, and then it determines the time they took for the trip to the trolley or to the object and back. Then this information is now passed to the computer, and the computer will now deduce the distance the object or the trolley moved, the distance to the trolley from the motion sensor, and then it will detect, or the computer will now generate what we call a distance time graph from this information. And then from a distance time graph, we can now determine the speed of the trolley. Of course, we know that in the speed will now be the gradient. Of course, the computer can also give the gradient, which we know that would be the speed in this case. So that's how a motion sensor works. So every time you talk about a motion sensor, especially in paper 5, you not talk about it in paper 2 or paper 1. But in paper 5, you tell the examiner that if you are in your planning or your experimental plan, you have mentioned a motion sensor, there must be a computer or a data logger. You don't need to give details of how really this works, but of course we know that the motion sensor sends some waves towards the object and receives the reflected waves. So the computer or the data logger will determine the time and the distance, and then it will sketch a graph of distance against time, from which the gradient is going to be the speed. Okay. And maybe one other method we may talk about, even though it has phased out, is going to be the ticker tape timer. The ticker timer or the ticker tape timer. The ticker tape. So this has a ticker and then a tape. This is a tape on which dots are always made on by the ticker. So what is special about this is that the ticker the ticker timer makes dots on the tape at regular intervals. It is usually a 1 over 50 seconds, that is a time of 0.02 seconds. After approximately 0.02 seconds, it makes a dot on the tape. In other words, it is vibrating. It is vibrating because it works using what we call alternating current which keeps changing direction, and because the frequency of alternating current is approximately 50 hertz. And I think 50 hertz is the same as 1 over 50 seconds. 50 hertz is the same as 1 over 50, because if you say 1 divided by 50, because frequency is equal to 1 over period, so 50 hertz is about 1 over 50 seconds. So it makes a dot onto the tape after every approximately 0.02 seconds. So our task is now just to analyze the distance between these dots to be able to understand or to make a judgment of the speed of the object or the speed of the trolley. You can also, by the way, do this on a falling object. You attach tape on a falling object. Of course, in that case, the ticker timer should be placed vertically so that it keeps on putting dots onto the tape when the object is falling. Okay, so the only thing we do for the ticker tape is we just inspect the pattern of dots which have been made onto the tape. So if we look at the space between the dots, then we can predict whether the object was moving at a constant speed, it was speeding up, or it was slowing down. The advantage of this method is that it can give us the instantaneous speed. It can give us an impression, it can tell us when the object was speeding up, when the object was slowing down. For example, this illustration here shows that the distance between the dots is increasing. Remember, all these dots are made after the same time interval. And if the distance between the dots is increasing after the same time interval, it means the object was now speeding up because it was now covering more distance in equal time intervals. So it was speeding up. So by examining the distance between the dots, we can determine the speed at any instant. That is how a ticker tape timer works. I try to demonstrate a ticker tape timer here. So we have a needle which is the ticker timer, which is going to put marks onto the tape. So we have three objects. One is stationary, one is going to be moving slower, and one is going to be moving faster. So our task is to inspect and analyze the dots which are formed. So compare the dots for a stationary object, the one which is moving slower and one which is moving faster. For a stationary object, the dots are made at the same point. Then for a slower object, the distance between the dots is smaller, and assuming the speed is constant, the distance between the dots is constant. Then for a faster object, the distance between the dots is bigger because the separation of the dots compared with the time will give us the speed. So we can say this one is moving faster because in the same time interval, the distance between the dots is bigger. And this one is moving slower because in the same time interval, the distance between the dots is smaller. So that is how a ticker tape timer is really is working. That's how a ticker tape timer is working. Okay, so one important thing you shouldn't forget is that if the separation between the dots is the same, then we say that the object is moving at a constant speed. If the separation between the dots increases, then we say the object is moving faster. If the separation between the dots decreases, then we say the object is slowing down. So in the first interpretation, the dots are equally spaced in the first diagram, so we say the object is moving at a constant speed. The second In the second scenario, the distance is bigger, but the separation is constant, so the object is moving at a constant speed still, but it is faster than the first one. In the second one, this is a wrong direction of motion, but we see that the distance between the dots is different. The distance between the dots is actually increasing. The distance between the dots is increasing. So increasing distance between the dots means the object is speeding up, and decreasing distance between the dots means the object is actually slowing down. So that is how a ticker tape timer really is supposed to work. So I don't want to spend much time on a ticker tape timer because this is not really going to be very important at this level. So finally, which method could you choose? Let's talk about choice of method. In the first unit of physics, physical quantities and units, the choice of method must have been a very important aspect of physics. And I said the choice of method depends on what you really want to achieve. How big is the distance being measured? For example, you can't use a micrometer screw gauge to measure the length of your table. You must use a meter ruler in that case. How big is the measurement being taken, and what precision or what accuracy do you want? So the choice of method will depend on what is really at stake. For example, what do you want really to achieve? So each of the above methods for finding the speed of the trolley has its merits. We have seen a light gauge, two light gates. We have seen a ticker tape timer. We have mentioned a motion sensor. Remember, all these are aiming at determining time because for the distance is very easy to determine using a measuring tool such as a meter ruler or a tape measure. So we are aiming at ensuring that the time measured is as accurate as possible in that case. So each of the above methods could be having some merits. That is, it has some advantages. So in choosing a method, you may think about the following points. For example, does the method give an average value of speed, or can it be used to give the speed of the object or the trolley at different points along its journey? So if you want an average speed, you can use ticker tape timer. I mean, you can use light gates. You can use light gates to get the average speed. You can use just a stopwatch and a meter to measure distance and time. But if you want instantaneous speed, you can't use light gates. You can't use a stopwatch. You'll instead choose a ticker tape timer. So, do you want an average speed or you want instantaneous speed? That is very important. The number two, how precise does the method measure the time to the nearest millisecond? If the distance considered is extremely small, then a stopwatch may not be a good choice for measuring time because there is a reaction time of a normal human being which may cause a lot of delays. So if the distance to be moved is very short or very small, you need a light gate or you need an automated method of determining time to give you a more accurate value of time. So how precise does the method measure the time to the nearest millisecond? So you must think about that before choosing the method. And number three, how simple and convenient is the method to set up in the laboratory? So you will not choose a method which is very hard to set up in the laboratory. But all the methods we have discussed are very easy to set up in the laboratory, even though now these days it is hard to find a ticker tape timer in the laboratories, but they should be there. They should be there. Okay, so that is all about measuring time. So I gave some common values of measuring time here. Even though you don't need to remember all of them, there's some common ones that should become part of you because in the unit called physical quantities and units, or in a topic called physical quantities and units, there's what we call estimates. You'll find questions of estimates in exams, especially question number 1, question number 2, question number 3, where they ask you to state an estimate. So some of these quantities will become part of you in physics as you go on studying physics. For example, At least we are much aware of the speed of light. We should also be much aware of the speed of a sprinter. A sprinter, such as Usain Bolt, is expected to run at around 10 meters per second, because the examiner may ask you to give estimates of the speed of a sprinter in a race. Then the walking speed of a normal human being is about 1.5 meters per second. The walking speed, 1.5 meters per second, because hours straight, a normal human old person is having a straight of approximately between 8 and 10 and 100 centimeters. So you are expected to make almost 1.5 straights in 1 second. That is the normal walking speed, about 1.5 meters per second. Then the speed of a jetliner should also become part of you, because many of you travel by plane. It's about 2,000, I think it's 250, approximately 250 meters per second. The speed of a jet airliner is about 250 meters per second. You can change this into kilometers per hour. Then the other common one could be this one, the speed of a car. You are driving cars every day. It is about 80 kilometers per hour, which is 22 meters per second. Then the speed of a snail, the snail is about 0.001 meters per second. And I say this unit is very big for the speed of a snail. So the speed of a snail is very, very small, about 0.001 meters per second. Then you may not really need to know the speed of an electron around a nucleus, but of course, the speed of the Earth around the Sun. But you can always predict 3 times 10 to the power of 4 as the speed of the Earth around the Sun. So some of these quantities will become part of you, or they are actually reasonable estimates. But I am expecting that a student who is living in everyday life must know the speed of light, the speed of a jetliner, airliner, the speed of a car on a highway, the speed of a sprinter, the walking speed, and the speed of a snail. Because the snail moves very slowly, the speed should be extremely small. Now, one important thing your teacher must have told that estimates are good enough to at least not more than 2 significant figures. You can't say the speed of a sprinter is 9.6763.3 meters per second. You can't say the speed of a sprinter is this, because these are so many significant figures. So the speed, any estimate is good enough to a maximum of 2 significant figures, because it's just an estimate. It can also be 1 significant figure. That's why you see all these values are not more than 2 significant figures. So these values could be useful when answering questions about estimates. So sometimes you may be asked to make estimates of several quantities. So some of these values may be very, very useful. Okay, let's talk about a few examples from the concepts we have just studied. The radius of the Earth is 6.4 times 10 to the power of 6 meters. One revolution about its axis takes 24 hours. Calculate the average speed of the point of a point on the equator relative to the Earth. So we want the average speed. They have given us the radius. That means they have not given us the distance. But of course, this is a revolution, so it is making one complete cycle about the center. So calculate the average speed of a point on the equator. So average speed is going to be the total distance divided by the total time taken. So I will write the answer work out here. So the average speed, I'll use V for average speed, is going to be total distance, which is going to be the circumference, 2 pi r divided by the time. So the circumference is 2 pi times the radius, which is 6.4 times 10 to the power of 6. Divide by the time is 24 hours, which has been given as 8.6 times 10 to the power of 4. Because it takes one revolution, so the time is the time of one revolution. So I'll just press my calculator. 2 pi times 6.4 exponent 6 divided by 8.6 exponent 4. So this is approximately 4.7 times 10 to the power of 2. So this is approximately 4.7 times 10 to the power of 2 meters per second. So that is the average speed of a point on the equator. How far does a cyclist travel in 11 minutes if his average speed is 22 kilometers per hour? At this level, I expect that each of us, we are old enough to be able to convert our units from kilometers per hour to meters per second. So we want to find distance, that is how far. So distance will be now the average speed times the time, that is the distance moved. So the distance is going to be the average speed times the time. The average speed is 22 kilometers, so I have to change it to meters per second. That is 22 times 1,000 divided by 3,600 to change it to meters per second. Then times time, which is 11. So I'll just press my calculator. So the average speed is approximately the distance is approximately 4,000 meters. I will check it again. 22. Oh, this is in minutes, so I multiply this by 60 to change it to seconds. So I got 4033. If you want, you can write 4033 meters, but it's approximately 4,000 meters. A train is traveling at a speed of 25 meters per second along a straight track. A boy walks along the corridor in a carriage towards the rear of the train at a speed of 1 meter per second relative to the train. What is his speed relative to the train? So the word relative means we subtract. We subtract. So a train is traveling at a speed of 25 meters per second along a straight track. So let's say the speed of the train is in that direction at 25 meters per second. A boy walks along the corridor in the carriage towards the rear of the train. So the boy is moving in the opposite direction. That is the rear of the train. No, the rear is the front part. So the boy is also moving in that direction towards the rear of the train at a speed of 1 meter per second. So the boy is moving at a speed of 1 meter per second. No, he's moving. The rear is the back side. Because when they say look at your rear mirror, it means look at the mirror which helps you to see at the back. So he's moving the other side towards the back. What is his speed relative to the earth? So we're just going to get the sum of these two speeds. So this is going to the relative speed is simply going to be 25 minus 1, which is 24 meters per second. If the boy was moving in the same direction as the car, as the truck, or as the train, if the boy was moving in the same direction as the train, the relative speed would be higher than 25. But if he's moving to the rear end, that is towards the back, then it means is the rate of speed between of the train to the boy is going to be lower. So if an observer is standing on the Earth's surface and looking at the boy moving backwards, he would see the boy as if he's moving slower than the speed of the train. But if the boy was moving to the front of the train, an observer standing on the Earth's surface will see as if the boy is moving faster than the train. As simple as that. So relative speed is just we shall subtract those two speeds. If it is in the opposite direction, it is just going to be -1. If it is in the same direction, it is going to be faster, so it will be +1. Okay, so I have a self-check for us. Here are some units of speed: meters per second, millimeters per second, kilometers per second, and kilometers per hour. Then we have miles per hour. Which of these units would be appropriate when stating the speed of each of the following? Remember, I said the choice of units will depend on the quantity being measured. If the quantity is very small, then a smaller unit is necessary. For example, the speed of a tortoise is very small, so the millimeters per second suits them. A car on a long journey can be kilometers per hour or miles per hour, but miles per hour is the best because um, it's a big unit. The speed of light, remember, light is 3.8 times 10 to the power of 8 meters per second. So this is a very large quantity. Therefore, the unit kilometers per second may be convenient. Then we have a sprinter. The speed of a sprinter is about 10 meters per second. So 10 meters per second may be fine. Then we have an aircraft. An aircraft travels at around 250 meters per second. So kilometers per hour may be a good unit, because if we change this, let me try to change that. So I'll say 250 divided by 1000 times 3600, because this will give us 900 kilometers per hour. This is 900 kilometers per hour. I think this will be a good unit. The best unit should give a good estimate to one significant figure. A snail crawls 12 centimeters in 1 minute. What is the average speed? This is basic. Average speed will be 12 centimeters. So I can change it to be, because they want this to millimeters per second, so I'll say 12 times 10, because 1 centimeter is equal to 10 millimeters, divided by 1 minute, which is 60 seconds. So you have 120 divided by 60, that is 2 millimeters per second. A trolley with 5.0 centimeters long card passes through a single light gate. The time recorded by a digital timer is 0.4 seconds. What was the average speed of the trolley in meters per second? So we have the distance, the length of the card, we have the time, we just divide. Let me check if this answer is correct. 5 divided by 0.4. A trolley with 5 centimeter long card passes through a single light gate. The time recorded by a digital timer is 0.4 seconds. What was the average speed of the trolley? So I think this is correct. Approximately 0.125 meters per second. The figure below shows two ticker tapes describe the motion of the trolley which produced them. So here we see that the distance between the dots are constant. So here we can say this is moving at a constant speed. or you can say zero acceleration. Of course, constant speed means no acceleration. Then here we see that the distance between the dots is increasing. So this is increasing speed. Because the dots are made after the same time interval, so the time is the same. But if the distance becomes bigger, it means the speed is increasing. So yes, increasing speed, or we can say accelerating. It is accelerating because increasing speed means acceleration. Four methods for determining the speed of a moving trolley have been described. Each could be adopted to investigate the motion of a falling mass. Choose two methods which you think would be suitable and write a paragraph for each to say how you adopt it for this purpose. So we have described the four methods above. We saw the single light gate, two light gates, we saw the motion sensor, and we saw the ticker tape timer. So each could be adopted to investigate the motion of a falling mass. Choose two methods which you think would be suitable and write a paragraph for each to show how you adopt it for this purpose. So this is going to be an assignment for you, but I think the ticker tape timer can work, where you attach a mass, the falling mass onto the tape. You have to attach the falling mass onto the tape, and then the timer, the ticker tape timer should be somewhere. So this should be the ticker timer. Of course, as it falls, the tape is pulled through the ticker timer and dots are made onto the what? Onto the tape. So attach the ticker tape to the falling mass. That's one method. You could also attach a card to a weight and drop it through a light gate. You could also you just reverse the same diagrams that we have, but in the vertical, because this is falling. So you have to you can attach a card to a weight and then drop it through a light gate. So you can write paragraphs for that. I've given you explanations previously. You can attach a card to a weight and drop it through a light gate. You can alternatively attach a ticker tape to the falling mass. So you can describe those methods. The speed of an electron in orbit about the nucleus of a hydrogen atom is about 2.2 times 10 to the power of 6 meters per second. It takes 1.5 times 10 to the power of minus 16 seconds for the electron to complete one orbit, actually the radius of the orbit. So one orbit is equal to the circumference. So they've given us the speed. So the speed is going to be equal to the distance, which will be the circumference, over the time. So we want to find the radius of orbit. So the radius of orbit is going to be the speed times time divided by 2 pi. So the speed is 2.2 times 10 to the power of 6, and the time is 1.5 times 10 to the power of minus 16. Divide this by 2 pi. I'll check and see if this answer is correct. 2.2 exponent 6, 1.5 exponent minus 16, divide by 2 pi. So this answer should be correct. The average speed of an airliner on domestic flight is 220. I think that is the same as about 900 kilometers per hour. How long will it take to fly between two airports on a flight path 700 kilometers long? So you have the speed and you have the distance. So you need to find the time. So the time will be equal to the distance divided by the speed. I will not calculate that, but I expect this to be correct. All we need to know is to change this from kilometers to meters, so that would be 700,000 meters. Two cars are traveling in the same direction on a long straight road. The one in front has an average speed of 25 meters per second relative to the earth. The others is 31 meters per second relative to the earth. So they are traveling in the same direction. So if they're traveling in the same direction, then the relative speed is going to be, I'm just going to subtract the two. What is the speed of the second car relative to the first when it is overtaking? So the person in the second car, because the one in the front has an average speed of 25. So the person in the car whose speed is 25 meters per second, we will notice see that the speed of the overtaking car is 31 meters per second, but the relative speed between them is simply going to be the difference between the two speeds, which is about 6 meters per second. That is 31 minus 25. So that is 6 meters per second. That is going to be the relative speed. So let's now talk about speed and velocity. Having done a few calculations or a few examples, let's briefly talk about speed and velocity. Just to try and compare them, we have been talking about average speed, instantaneous speed, and so on and so forth. So now let's talk about speed and velocity, and we see what is the difference between the two. So what is velocity and what is speed? We have talked about speed as distance divided by time taken, or we saw the average speed as total distance divided by the time taken. So we know that velocity is a vector quantity from our first topic of AS physics, and it is actually the speed of an object, but this time the direction is going to be given. So velocity represents the speed of an object and the direction in which it is moving. So the two are very important, which means speed is a scalar quantity, and we normally prefer to say that speed is the magnitude part of velocity. Remember, if direction does not change, speed and velocity will be the same. But if direction changes, speed and velocity will not be the same. So the average velocity could be the displacement divided by the time taken. Now note the difference between speed and velocity. When we were calculating the average speed, we saw that it was the total distance over total time taken. Then for the average velocity, it is going to be displacement divided by the time taken. Remember, displacement is the straight line distance. So we just get the first point and the final point, and we get the straight line distance between the 2 points. Yet for speed, we must sum up the distances between the distances between several parts until we reach the final point. So average velocity is going to be displacement divided by time taken. And if we consider motion from say a point x1 to point x2 without change, there is no change in direction here, but even if there was change in direction, so the displacement is going to be x2 minus x1, and the time taken here, we'll say, let's say the time at x1 is t1 and the time at x2 is t2. So the change in time here is going to be t2 minus t1. So the average velocity is going to be the change in the displacement over the change in time. So average velocity is going to be x2 minus x1 over t2 minus t1. We just get the final position minus the initial position divided by the total time between the two positions. So that's why we say we don't mind about the direction. We are just interested. I mean, we don't mind about the length of the path. We are just interested in the direction because we want the straight line distance from the starting point to the final point. So velocity will either be negative or it will be positive depending on the direction, because velocity is a vector quantity. So velocity can be positive or it will be negative, but speed will always be positive. So when we talk about speed alone, because it is a scalar quantity, we shall always consider it as being a positive, only positive. So let's summarize the difference between speed and velocity. So to differentiate the two, speed is the rate of change of distance, that is distance divided by time taken, and is a scalar quantity. Yet velocity is going to be the rate of change of displacement. Now many times we make a mistake and we say velocity is the rate of change of displacement with the time or per unit time. That is a repetition which cancels out the word rate, because the word rate means a change in displacement over time taken. So when you say rate of change per unit time, you are cancelling out the part of rate, because rate alone means pi with respect to time. So velocity is the rate of change of displacement and it is a vector quantity. Yet speed is the rate of change of distance and it is a scalar quantity. Of course, they have the same units, but one is a scalar and one is a vector. In defining the speed, we consider distance. In defining the velocity, we consider displacement. Mark those two differences very well. In calculating speed, we consider the distance. In calculating velocity, we must be very specific and we use the displacement. However, if there is no change in direction, distance and displacement are the same. Therefore, the velocity and the speed will also be the same. So we are saying, because distance and displacement are different quantities, the average speed of motion will sometimes be different from the magnitude of the average velocity. Distance and displacement are different quantities, especially if there is a change in direction. Therefore, the speed and the velocity will also be different, especially if there is a change in direction. So we are going to understand this by considering this example. So let's consider a cyclist traveling 500 meters due east along a straight road, and then turning around and coming back 300 meters. So you might ask yourself, what is the average speed and what is the average velocity? So to understand average speed, we have to find average speed. We need the total distance divided by total time. So for total distance, we shall have 500 plus 300, which will be 800. And the time, let's say the time is t. Then let's compare this with the average velocity. So for average velocity, average velocity will be now displacement divided by the time, or change in displacement divided by the time. So to the it moves 500 meters to the say to the left, to the right, and 300 meters to the left. So it means to the right, if to the right is positive, then to the left is going to be negative. So total displacement is going to be 500 minus 300, which gives you 200 meters. So it means the average velocity here will be 200 meters divided by the time, if we are considering the same time. So you notice that the average speed is going to be bigger than the average velocity, because the total distance is bigger than the total displacement. So you should know the difference between those two, velocity and speed, or average velocity and average speed. They are not, if there's a change in direction, they would not be they would not be the same. Okay, so note that this difference arises because of direction, and if there was to be no change in direction of the motion, then the speed and the velocity at that moment would be or would remain the same. it would remain the same magnitude. But if there is a change in direction, I want you to be very careful to note that whenever there is a change in direction, the distance and the displacement are not going to be the same. And if the distance and the displacement are not going to be the same, it also means the velocity and the speed will not be the same whenever there is a change in direction. So I think that should become part of you. Whenever there is a change in direction, the velocity and the speed will not be the same because the distance and the displacement are not going to be the same. Whenever there is no change in direction, the velocity and the speed will be the same because whenever there is no change in direction, the speed, I mean the distance and the speed and the displacement are the same. That is very, very important. Okay, more example. So when an object is moving in a circle at a constant speed of say 10 meters per second, we say that it has a constant speed, but we can't say that it has a constant velocity, not at all. The reason is because remember speed is a scalar quantity and it could be the magnitude part of velocity. Any object moving in a circle, it keeps changing direction. For example, if it is moving in that direction at this instant, when it is here, it is going to be moving in this direction. When it is here, it will be moving in that direction. When it is here, it is going to be moving in that direction. So it is always moving at a tangent to the circular path. We shall see this under circular motion in year 2 in paper 4. Or if you are doing both AS and A level, you must have seen this under circular motion. That an object moving in a circle always moves at a tangent to the radius. Always moves at a tangent to the radius. Its speed is always at a tangent to the radius. Therefore, there is always a change in direction. Even if the speed is constant, there's a change in direction. And since velocity is the speed in a specified direction or the rate of change of displacement, yet displacement is distance in a specified direction, then it means whenever an object moves in a circular path, even if it is moving at a constant speed, its velocity is not constant because there's a change in direction. So for a body moving in a circle, its direction keeps changing. And since velocity does not only depend on magnitude but also depends on direction, so it means uh, even though the magnitude may not be changing, but the direction is changing, so it means the velocity keeps changing. That's why we say this body has an acceleration, which you may call the centripetal acceleration, or you might have called the centripetal acceleration in circular motion, because there's a force which continues keeping the object moving in a circle, which you may call the centripetal force, which gives the centripetal acceleration. So there's an acceleration even when a body moves at a constant speed in a circular path, because there's an acceleration because the velocity is changing. But how is the velocity changing when the speed is constant? It's because of direction. The direction keeps changing, and changing direction is enough to imply that the velocity keeps changing. So whenever an object moves in a circular path, its direction keeps changing. And if the direction keeps changing, then we simply say the velocity is changing. Okay, so that is velocity. Let's briefly talk about acceleration. Remember, we are still describing motion in using words. We have seen distance and displacement. We have seen speed and velocity. Now let's talk about acceleration. Still from IGCSE, you defined acceleration as the rate of change of velocity. It is the rate of change of velocity. That is change in velocity per unit time, or change in velocity over time taken. That is acceleration. You also mentioned that acceleration is a vector quantity in IGCSE because its direction depends on the direction of the resultant force. Acceleration is a vector quantity because its direction depends on the direction of the resultant force. So because the acceleration is the resultant, acceleration is the rate of change of velocity, so we shall need an initial velocity and the final velocity of a body, and then the time taken. So final velocity minus initial velocity divided by time. This would give us the acceleration of a body, and this is the same equation used in GCSE. So note that when a body slows down, it means the final velocity is smaller than the initial velocity. And this would give us a value which is negative for the acceleration. And a negative acceleration, you must have called it a retardation or a deceleration. A negative acceleration is often called a deceleration. We know the units of acceleration from GCSE as meters per second squared. They are still the same units. For example, a sprinter might have an acceleration of 5 meters per second squared. This means that her velocity increases by 5 meters per second every second. That is, if the acceleration is 5 meters per second, when you break this down, it is 5 meters per second squared divided by seconds. So it means in 1 second, the velocity increases by 5 meters per second. And the acceleration of free fall near the Earth's surface is 9.81 meters per second squared, and we are aware of this, which means if air resistance is negligible and an object is falling, in every second, the speed of the object increases by 9.81 meters per second in every second. That is acceleration. Okay, so let's explore a few questions which require us that understanding. These are GCSE questions mostly, so most of them I will not answer them fully because this is a self-check. You can always pause the video and try to practice and see if you recall the concepts of GCSE that we are using here. Leaving a bus stop, the bus reaches a velocity of 80 meters per second after 10 seconds. Calculate the acceleration. We have said acceleration is equal to the final velocity minus initial velocity divided by t. So leaving a bus stop, the bus reaches a velocity of 80 meters per second. So leaving a bus stop, it means initial velocity is 0 and final velocity is 80 meters per second. The time is 10 seconds. So I will just substitute and see if the answer is correct. 80 minus 0 divided by 10. I think this is correct. A sprinter starting from rest. From rest means initial velocity is equal to 0. Has an acceleration of 5 meters per second. So this is A. The time during the first 2 seconds. So T is 2 seconds. Calculate her velocity after 2 seconds. So just substitute in A equals to V minus U over T. A train slows down from 60 meters per second to 20 meters per second in 50 seconds. Calculate the acceleration, the deceleration. So here you expect to get a negative, and the negative simply means the deceleration. So the deceleration is going to be equal to final velocity minus initial velocity divided by time. So that should give you that answer. A car accelerates from a standing start and reaches a velocity of 18 meters per second after 6 seconds. Calculate its acceleration. So it accelerates from a standing start, which means initial velocity is equal to 0. So the acceleration is going to be the final velocity, which is 18 minus initial velocity divided by time, which is 6. A car driver brakes gently, her car slows down from 23 to 11 in 20 seconds. Calculate the magnitude of her deceleration. So the deceleration is going to be the final velocity minus the initial velocity divided by time. You expect the answer to be negative because it is a deceleration. A sport car accelerates along a straight track from 70 kilometers per hour in 6.3 seconds. What is its average acceleration? So it starts from rest. A sport car accelerates along a straight track from rest 70 kilometers per hour in 6.3 seconds. So the average acceleration is going to be, we have to just change 70 kilometers per hour to meters per second. And this would be 70. So final velocity is going to be 70 times 1000 divided by 3600. That is the final velocity. So the acceleration is going to be 70,000 divided by 3,600 minus the initial velocity, which is 0, divided by 6.3. And I think this answer should be correct. Let me check. 70,000 divided by 3,600 divided by 6.3. That answer is correct. You can stop the video and try to practice this because they are not really very important questions for this level. A stone is dropped from the top of a cliff. Its acceleration is 9.81 meters per second. How fast is it moving after 1 second? So remember, this statement means the speed increases by 9.81 meters per second every second. So it means after 1 second, this is going to be 9.81 meters per second. Then after 3 seconds is going to be 9.81 times 3, which would be 9.81 times 3, which would be 29.43 meters per second. Because if we say the acceleration is 9.81 meters per second, it means per second squared, it means the speed increases by 9.81 meters per second every second. So here, 1 second, the speed increases by 9.81 meters per second. So it means after 3 seconds should be 3 times 9.81. A railway train traveling along a straight track takes 1.5 minutes to come to rest. So this is 1.5 times 60 to change it to seconds. From a speed of, because it is coming to rest, it means final velocity is equal to 0. From a speed of 115 kilometers per hour, so this should be changed to meters per second. So this would be 115 times 1000 divided by 3600 to change it to meters per second. What is its average acceleration while braking? So the acceleration is going to be the final velocity, which is 0, minus the initial velocity, which is 1, sorry, to come to rest from this speed. So the initial velocity is going to be 115 times 3600, times 1000 divided by 3600. That is the change in velocity, divided by the time, which is 1.5 times 60. Let me check if that answer is not correct. So we have negative 115 times 1000, 3600, 1.5 times 60. Here it is. I think that answer is correct. A sprinter starting from the blocks, that means initial velocity is 0, reaches his full speed of 9.8 meters per second in 1.5 seconds. What is the acceleration? So acceleration is going to be final velocity minus initial velocity divided by time. A car is traveling at a speed of 25 meters per second. At this speed, it is capable of accelerating at 1.8 meters per second squared. How long would it take to accelerate from 25 meters per second to the speed limit of 31 meters per second? So a car is traveling at a speed of 25 meters per second. At this speed, it is capable of accelerating. It is capable of accelerating at 1.8 meters per second. How long would it accelerate from 25 to 31? So we want the time. Acceleration is equal to final velocity minus initial velocity over time. So we want time. So t is going to be v minus u over the acceleration. So this is going to be 31 minus 25 divided by 1.8, which I think should give us 31 minus 25 divided by 1.8, 3.3. So the time should be, sorry, this is times 3.3 seconds. At an average speed of 24 kilometers per hour, how many kilometers will a cyclist travel in 75 minutes? So we want the answer to be in kilometers, and that is distance, by the way. So the distance is automatically speed times time. So this is going to be, the speed is 24 kilometers per hour times the time. I must change the time to hours. Remember, 1 hour is 60. 1 hour is 60 minutes. So it means 75 minutes. 75 minutes is going to be 75 minutes is going to be equal to 75 divided by 60 hours. So this will be times 75 over 60 hours. So the units hours have cancelled out. So I have 24 times 75 divided by 60. So this is 30 kilometers. An aircraft travels 1,600 kilometers in 2.5 hours. What is its average speed in meters per second? So you just change the time to, so this would be to seconds, this would be times 3,600. This one to meters to be times 1,000. So the speed is going to be 1,600 times 1,000 divided by the time, which is 2.5 times 3,600. That is distance over time. So 1,000 1,600 times 1,000 divided by 2.5 times 3,600. So this is approximately 180 meters per second to two significant figures. Does a car speedometer register speed or velocity? So the car speedometer does not tell the direction, so it registers speed, not velocity, because it doesn't give us the direction. It just shows us a magnitude on the screen. So the speedometer does not tell us the velocity because it doesn't give us the direction, so it just tells us the speed. An aircraft travels 1,400 kilometers at a speed of 700 kilometers per hour and then runs into a headwind that reduces its speed over the ground to 500 kilometers per hour for the next 800 kilometers. What is the total time taken for the flight? What is the average speed of the aircraft? So for the first, an aircraft travels 1,400 kilometers at this speed. So the time here is going to be, let me call this one T1. Time 1 is going to be distance over the speed. We are using a distance, or speed is equal to distance over time. So time is distance over speed. So T1 is going to be 1,400 divided by 700. For the first journey, it is 2 hours. And then runs into headwind that reduces speed over the ground 500 kilometers for the next 800 kilometers. So the second journey, I'll call this one T2. T2 is going to be equal to 800. T2 is going to be 800 divided by the speed, which is 500. So this is 1.6. 1.6 hours. So for the first journey it takes 2 hours. For the second journey it takes 1.6 hours. So the question is find the total time for the flight. So total time is going to be 3.6 hours. That is total time. Then for the average speed, so the average speed is equal to total distance divided by total time. So this is going to be total distance is going to be 1,400 plus 800, which is I think 2,200 kilometers divided by total time, which is 3.6 hours. So 2,200 divided by 3.6. So this is 611 meters per second, or approximately 610 meters per second as the average speed of the aircraft. Total distance is total distance divided by total time. So I think the average speed is going to be approximately 610 kilometers. 610 sorry, it is kilometers per hour. Okay. A sports car can stop in 6.1 seconds from a speed of 1,100 kilometers per hour. What is its acceleration? What is its acceleration? So you have the time. They said it can stop. It means final velocity is 0. So the acceleration is going to be 0 minus. You have to change this from kilometers per hour to meters per second. So it will be 110 times 1,000 divided by 3,600. That is the change in velocity divided by time, which is 6.1. So 110 times 1,000 divided by 3,600, then divide by 6.1. This is approximately 5.0 meters per second squared, and to be negative, I'll check it again. 110 times 1,000 divided by 3,600 divided by 6.1. Okay, so that is correct. Then can the velocity of a particle change if its speed is constant? Can the speed of a particle change if its velocity is constant? If the answer to either question is yes, give examples. So can the velocity of a particle change if its speed is constant? Yes, because velocity depends on the direction. If speed can remain constant, but if direction changes, the velocity changes. Then can the speed of a particle change if its velocity is constant? If the velocity is constant, the speed is not changing because speed is the magnitude part of the velocity. So for the first part, if the velocity changes, velocity can change if the speed is constant because the direction could change. Velocity also depends on direction. But if the speed is constant, the speed cannot change, because if the speed is constant, it means both the magnitude and direction are not changing. So the speed is the magnitude part of the velocity. So if velocity is constant, the speed is constant. But if speed is constant, velocity can still change because velocity also depends on the direction. Velocity also depends on the direction. Okay. So before we summarize lesson 1, you need to recall to note a few um, estimates of the acceleration of different bodies. We know the acceleration of free fall is 9.81, but if it is an estimate, it is always going to be about 10 meters per second squared. So acceleration of free fall, 10 meters per second. I think the acceleration of a family car is around 2 meters per second squared. The acceleration of free fall on the moon, on Earth, acceleration of free fall is g. which is 9.81, which is approximately 10 if it is an estimate, meters per second squared. On the moon, this was on the Earth. On the moon, it is at a sixtieth of this, which is approximately 1.6 or 2 meters per second squared. That is the acceleration on the moon. Then that is acceleration of the moon, or acceleration of free fall on the moon. Then the acceleration due to the rotation of the Earth around the equator, I think it's around 3 times 10 to the power of minus 2 meters per second squared. The acceleration due to the circular motion of the Earth around the Sun is about 6, I think, times 10 to the power of minus 5. The acceleration of a car crash, I think, is around 1,000 meters per second squared, I think. The acceleration of a family car is approximately 2 meters per second squared. If you look at the speed, the distance, or the estimated distance of 80 kilometers per hour, the acceleration of a family car is around 2 meters per second, I think. So you should have an idea about the estimates of some of these quantities, especially acceleration of free fall, that is acceleration due to gravity on the Earth and on the moon. Then you should have at least an idea about the acceleration of free fall of a family car. For a family car, it is about 2 meters per second. I think those are the only estimates you need to recall at this level. Okay, so let lesson 1 stop here, I think. See you next time.